Alright, here we're going to review some of the topics we talked about previously in the first couple of lectures. Here I'd like to talk a little bit more about the scientific method. And here are kind of your steps to the scientific method. We talked about the fact that Darwin was a natural historian. He was not technically a biologist, a scientist in the real sense, because Darwin did not complete this list here. He came up with the theory of evolution, but to really do hard science that we're kind of going to be talking about here, you need to go ahead and be able to do experiments. And if you think about it, yes, Darwin did make observations. He also asked questions. Why do these things happen? You know, he looked at the animals and he saw they were similar in certain ways, but on different islands they were slightly different. They had adapted essentially to the particular island that they were on, so they were slightly different than the others. And he made that observation, and he asked himself, what's causing this? Alright, so he asked some questions, and he did form a rudimentary form of hypothesis. So he was good. He did all three of these. So he was halfway there, but because he didn't do any experiments to test his hypothesis and then draw conclusions from that, and then of course he did communicate his ideas, and he wrote a book, but he was not able to actually test his hypothesis with experiments, and thus we can't say he completed this list of things, and so Darwin remains a natural historian, and thus it's pretty much what we call soft science at best, or it's really just natural history is not considered a science. So we really can't say that Darwin was a scientist. He was a natural historian. He was an observer, and a natural historian is similar to someone who's like a bird watcher or a bug collector or something like that. Now he did make some really good hypotheses, but he didn't quite go the full way of proving any of his conclusions that he made. He needed to do experiments. Now there is something else though he did come up with. He came up with the concept of natural selection. And later on, people did come up with experiments that can prove in the laboratory without a doubt that natural selection does occur. And evolution, though, is something that occurs over millions of years, lots of time, lots of changes in the environment. You have to wait for those organisms to adapt to it. So you're probably never going to prove evolution as a concept, but you absolutely can prove natural selection. And so evolution is the logical consequence of natural selection. We can prove natural selection, and then logically you say, well, you know, if we let this go on for millions of years, what do you think would happen? And most people would say, yeah, it'd be something kind of like what we call evolution. So the idea of evolution can never be proven, but the natural selection can. And since natural selection can, you just kind of, in your own mind, go, well, what would happen if we let this go on for a long time? And you would, of course, come to the conclusion, probably, I mean, that's what most scientists have done, most biologists. They've said that, well, evolution exists because this kind of makes sense if you let this go on for a long time. Proving it, that would be another matter. Like I said, if you invent a time machine, you could probably prove it. But at this point, we have no time machines. The best thing we have are fossils, and things that are in the geological record where they have stored information over millions of years, and that's what we usually use to support the concept of evolution in biology. Alright, so let's go on a little bit further here. We have the scientific method. This is what you do in the scientific method. You have a kind of a cycle here that you go through with inductive and deductive reasoning. We'll talk a little bit more about that in a second. But the idea is you have your explanation and your theory. They have a prediction that you make. You do an observation, an experiment, and then you you come back and you generalize it to the entire population, for instance. You see a few organisms do it, and you go, I'll bet most of them do it, and I bet this is a law or something. We'll kind of set this down as the way it works. And then once you've done that, you say to yourself, well, how can I test it to prove if this is always the case? And you change what are called variables, and you do an experiment, and then you look to see if it works. So this is kind of your idea of your scientific method in a more general sense, where you have your theory up here and your experiment down here, and you do observation. Then you have your explanation. You come up with your theory that goes along with your explanation, and then you predict something and you do an experiment to see if your prediction comes true. So this is the cycle for the scientific method, and you need to know that. You need to know that which ones come on the inductive side, which are along here, which ones come on the deductive side, which are along here. Alright, now we have what we call our hypothesis. Our hypothesis is kind of like our theory. We've observed some things and we've come up with a theory, and we have to come up with a way to test our theory. So this is a general rule. So our example here is being a rabbit makes you run faster than being a turtle. I think that observation would be one that we would all agree on is true. So you would go, your hypothesis predicts a cause and effect. So the reason something happens and the result of what happens. So what you might do is set a race. There's the famous between the rabbit and the hare. The tortoise and the hare, turtle and a rabbit. And of course, the wrong one won. If your theory would be that the rabbit would win in that story, if you know that story. But the rabbit stopped along the way, and the turtle just, steadily walked through. And since the rabbit knew he could win because he was faster, he didn't pay much attention, and he accidentally let the turtle win the race. And so if your prediction was, well, the rabbit will always win the race, that would be incorrect, right? You would have not been able to prove your hypothesis, but your hypothesis was that the rabbit runs faster. And I think it's very obvious that the rabbit does run faster. It's just that you somehow have to keep the rabbit on the track and not stopping along the way for a carrot or something. All right, but this is your idea. Your hypothesis is that the rabbit has more powerful legs and things like that, weight to strength ratio sort of thing, and so maybe you predict that because of this, your hypothesis is that the rabbit will win the race, and the cause, of course, would be the muscle strength, and the effect, the results of what happens are that the turtle doesn't win, the rabbit does win. And so this is how you would come up with your hypothesis. Now, it's interesting. Let's note that a hypothesis is a statement or an assumption about a relationship between variables. So that means we have variables. So what are our variables? Well, you'll have variables that are fixed, all right, and don't change, that you're not going to be able to change. They're kind of like maybe the result. You win or you lose. And what can you do to alter it? Well, you might be able to change a variable. Maybe you, in this case, you have rabbits and turtles. There aren't very many variables that you can change here. You might want to test whether or not they run faster in hot or cold weather or something. There might be some variables you could alter and see if you can test. Maybe the turtle is really fast in the warm weather. I doubt that, but maybe that would be one of your assumptions for some reason. So you might do this in higher temperatures in the summer, and then you might test it in the winter and see if there's a difference. But that would be a slightly different hypothesis than just the rabbit is faster. All right, but there will be variables that you can change. So you have fixed variables and you have variables that you can alter, like the heat. You could alter the heat. That's a variable, but you can't. The fixed variable would be who wins the race. More like the turtle wins or the rabbit wins. That's your fixed variables. Now it is a tentative explanation for certain behavior or phenomenon that have occurred or will occur. So this is your explanation, that's your hypothesis, and then you're going to alter variables and see if the outcomes you predict are true or do occur, and that would be how you set up your hypothesis. There's also something called a null hypothesis that we will talk about now later in the course. I may get to it here. Here are some hypotheses. You have chocolate may cause pimples. Notice how they put may in here. Hypothesis is not proven. In fact, you never prove your hypothesis. You can disprove your null or prove your null hypothesis, the other types of things that we talk about, but you can never prove a hypothesis. You can never prove this, so keep that in mind when you're doing this. Make sure you don't say you proved your hypothesis, because that would be an incorrect statement and you'll get counted off for that. So chocolate may cause pimples, salt in the soil may affect plant growth. Alright, plant growth may be affected by the color of the light. Bacterial growth may be affected by temperature. Ultraviolet light may cause skin cancer, and temperature may cause leaves to change color. All of these are theories about how the world works, and there are variables you could alter to test this. For instance, you might take two groups of people, and you might feed one group of people chocolate, and the other one you feed no chocolate, and then you might look to see which one has more pimples. Salt in the soil would be easy. You could either put no salt or a lot of salt, or maybe you could put varying amounts of salt. And if you did, and you saw that the more salt you put, the slower it grows, that's a very good. Not only does it show that yes, it affects the growth, but it affects it maybe in a direct manner, as in the more salt you put, the smaller it is. If you put slightly less, it grows a little taller. It's not just an all-or-one type thing. There is a gradient, you might say. Something that's like a linear straight line that would show on a graph that, okay, a lot of salt, you get zero growth or little growth, and then as you reduce that amount, you get more and more growth. But of course, there might be the fact that maybe the plant needs a little bit of it. So when you get down close to zero, maybe you get in. If you did take it to zero, maybe the plant doesn't grow at all. And so that would be, your hypothesis would be, of course, if you said that the more salt, the less it grows, and then of course you realize you take it to zero and it doesn't grow at all, you would have to alter your hypothesis and just say what they say here. Notice, what do they say here? It affects plant growth. It didn't say that that it couldn't have salt, or salt is a poison, or salt always the more salt, the less it grows. It said it affects. So the thing is, salt in the soil may affect it. That means it might make it go either way. You notice you didn't say that it went in one particular direction. You said that it just affects it. And so that means by altering the amount of salt, maybe there's an optimum amount, all right, and it's somewhere in the middle. And so that way you're safe in this hypothesis to say this, and all you have to show is that when you alter the salt amount, it does alter the growth. You didn't say up or down. So that's a key later on for setting up some of these hypotheses, is that make sure you're careful what you say, because it might be very easy for you to make a mistake. And a lot of scientists make this mistake. They'll make a very bold statement, and maybe they shouldn't have made it like the statement that it always happens or something like that. It just may happen. So it's very important to understand how to write a good hypothesis so that it actually is not easy to disprove, because if you write it wrong and people don't like what you're saying, they can easily disprove it if you didn't state it correctly. Alright, now we go back to this concept of deductive and inductive. Deductive, you're gathering information, you're looking for patterns, you create a tentative hypothesis in theory, but you're not trying to confirm it. You're just kind of watching and and coming up with general ideas. On the inductive side, you already have an idea. Alright, your idea is already fixed in your head. You think this is the way the world works. You're not over here in the deductive side. You're trying to figure out your theory. Over here, you have your theory, and you're trying to test your theory. So over here is where you do your experiments. Over here is where you're doing the observations to come up with a theory. So that's a good way to do this. Is coming up with a theory, and this is testing your theory. So you have a hypothesis and observation. It means you probably did an experiment here, and after you observe the results of your experiment, then you have confirmation that yes, indeed, it did what I wanted, or it did not, and you can say that your theory was correct. Alright, again, a little bit more on the inductive and deductive. I'd say this is one of the harder things for people to get, actually, is kind of like, well, what exactly do these mean? So like I said, inductive derives general principles from observations. Now, right here. So if you're talking about observations, you're probably talking about inductive reasoning. Alright? And you're like, well, I think all living things are made out of cells. Alright? And your deductive reasoning is when you're going to experiment on, do an experiment to test this. If all organisms are made of cells and human, this is an example of using that kind of logic. This is not how you make an experiment. This is just trying to help you define what deductive means versus inductive. A lot of times it's very difficult if you're watching a detective. Is a detective using inductive or deductive reasoning? And when they're doing inductive reasoning, they're coming up with a theory from what they noticed. But if you'll notice over here they're coming up with a conclusion based on what they observed. They said, well, if this guy if he was at this place at this particular time and there was no one else there, then he must have committed the crime. Whereas over here, you're trying to prove where he was. So if you have this bad guy in a movie and you're trying to figure out if he was at the scene of the crime, that's probably more inductive reasoning. But then when you say, well, if he was here, there was no one else here, then there's no one else to commit the crime, he must have done it. That's the deductive reason. It gets complicated here in these concepts. So be careful when you're doing this. Try to make sure you have this set up in your mind correctly. Alright, so the next one here, we're going to the natural hard sciences, and so I talked about it briefly in the previous lecture where there are hard sciences and soft sciences. Your harder sciences are things like physics, maybe you'd consider math a science, chemistry, and those would be the two, especially physics and chemistry. Those are the ones where you do lots of experiments and you don't do much, you don't have to guess much, I guess is the way you would say it. You do the experiment and it either does what you want or it doesn't. And it's easy to do experiments with physics and chemistry. Now, math technically is not a science. Math is actually a branch of philosophy. A specific branch of philosophy as well. So you really don't consider it in the sciences. It's actually considered a branch of philosophy when you actually get down to how they classify these things. But in the hard sciences, when they talk about the hard sciences, math gets used so much that it gets lumped in here. So technically I'd say this is technically an incorrect statement when it says math right here, but we'll let it slide. Considered pure, standalone, unique bodies of knowledge. Not important for what we're doing. I'm more interested in realizing that physics and chemistry are the hardest sciences. And this is really, once you do the experiments and you get the results in chemistry and physics, there's not much arguing with it. You can reproduce it, and over and over again, you can pretty much be sure that that's the way it works, and it's, that's how we do chemistry and physics, and it's no one questions this. Now there can be additional things discovered later, but you don't get a lot of surprises in physics and chemistry. You find this in medicine a lot. Diseases focus rather than on person. The whole idea here is that physics and chemistry are definitely hard sciences, because you can do really good experiments that are reproducible over and over by different people and they get the same results. Now we move on a little bit. Talk about hard science. Hard science is easy because of these things. You can replicate it, and there aren't any external forces changing your results. It's easy to control the environment in physics and chemistry, but say you get to biology, well, biology has living things in it, and that throws a monkey wrench into almost everything. It makes it really difficult to always control the environment around an organism, because the organisms are trying to survive and adapt, and they learn. So you can't use the same rats over and over again because they learn, that sort of thing. And the biochemistry might adapt to a drug, so you can't keep using the same rats to see how they react, because over time they may react different. There are all kinds of things that make it difficult to use living organisms, and so that will reduce the hardness, as we say, of the science. And if you want to think about sciences that are not hard sciences, the soft sciences have a hard time doing experiments. So, for instance, astronomy. Can you go do experiments out with planets and stars? I mean, that's what your heavenly bodies are what you are studying in astronomy. And it's really hard to go out and do an experiment on these things. You can do some physics experiments on light and things that are related to astronomy, but to actually do an experiment in astronomy, you would have to do what? You would have to be able to manipulate things like stars and planets, and of course we can't do that. So we're kind of like stuck like Darwin was. He observed and he came up with ideas, but can you prove that the planets are going to behave like this in the future? Well, the physics are pretty good on the small scale, but on a large scale, no one's ever shown that does gravity really work the same way with planets and stars as it does with, like, say, at a micro scale, and we just haven't been out there. There's no guarantee. Someone pointed this out to me once. There's no guarantee that the laws of physics or the laws of chemistry or anything hold up out in space. Since we've never been there, you don't know what the laws are until you get there. And so, that's kind of the idea. All we know is what happens here on Earth. Maybe there are things that behave differently at different parts of the universe. Now, they don't think this is the way it works, but there's no guarantee until we go. So maybe gravity is different the further away you get, or maybe light can travel at a different speed at different parts of the universe. We assume that what happens here happens elsewhere, but since we've never been there, we can't prove it. So that's a problem, but we assume that it's going to be the same. Now, with living things and with things that you can't do experiments with, we of course call that soft science. Astronomy, really hard to do experiments with planets and stars, so it's a little soft. I know the astronomy professor here at Lone Star would argue with me that, we're a science, and, if we go by the exact definitions, if it's science, it's a very soft science. No experiments. That makes it soft. Alright, so let's move on here. Science and technology are related. How is science different from technology? In science, we do experiments. That's the whole idea of science, and we come up with theories. Technology is the application of what we learn. So we learn that, if we could hit that nail exactly on the center of the head of the nail, it would go in straighter. So we know that from doing physics. We go, okay, if we can hit it right there exactly, it's going to go in straighter, and it's going to have a better fit, and your house is going to be better. So we come up with a technology to do exactly what our theory says. Our theory says if you can hit it straight on, it's going to be a better hit, so we develop something that hits it straight on. So here the science tells us this is the way the world works, and then we invent something to utilize that theory to achieve some goal, which is to make a better house, and that's technology. So these go together, and often the technology we develop will help us in science. So in physics, you invent lenses, which then help you in astronomy or in biology, making microscopes or telescopes. And by figuring out with physics how to build a better microscope, for instance, you've improved biology. And so the technology, is derived from science, but then the technology also helps you in advancing science, and we call this progress. Alright, and I think our last one here, examples of science. We do theories, what causes the flu, which of course is a virus. How are atoms put together? Well, we figure that out through essentially smashing them together. How is genetic information stored and transmitted? Well, we did that by looking and seeing if we alter the DNA, did the organism change? If we alter the lipids or the carbohydrates, or if we alter the proteins, which of those can cause a change in the organism? And then once we figured out, okay, we might alter the protein and the DNA, and they both cause a change in the organism, but then we change the protein, and it doesn't pass down to the next organism. But we change the DNA, and then it is passed down. We know that the thing that carries the genetic information is the DNA. Alright, so an example of technology that deals with the flu is a vaccine. Of course, learning about the structure of the atom, let us build atomic bombs or atomic energy. And of course, once we understood how information was transferred, we learned to manipulate DNA to do genetic engineering. So all of these are results of, we do the theory first and then develop a technology around it. And then that technology thing can also come back and help us do more things in science. As we learn more and then we build better tools, then we learn more from using those tools, and then we can come up with even better theories. And this is what we kind of call progress. And it's the relationship between science and technology. This does it for this video. This is just a follow-up on that very first couple of videos where we were talking about these subjects. I just wanted to go into a little more detail with these.